Thanks, Phil, once again. And thanks for showing up, such a large audience. It's always a pleasure to talk to lots of people. Okay, my talk has a fairly broad topic. It's 2D and 3D image processing, and obviously I cannot cover everything that we have done lately regarding this topic. So I will proceed as follows. Once we are done implementing all these commands, we are asked to generate marketing pages, or come up with examples that show applications of our new implementations. So basically what I will do now is simply give you two examples of how you could apply existing and new image processing commands in Mathematica on two applications, and just introduce them as we go. All right, I'll just simply start in my first section with 2D images, but in a way I will add a third dimension, that is time. And what I'd like to implement here is a pulse meter. I'm not sure if you have seen apps like this on the web. There are companies like Philips introducing them, or universities like MIT. The idea is simple. If a person stands in front of a camera, we can try to measure the pulse, the heartbeat, and we do that simply by looking at the skin. And the skin tone does change very minutely, very slightly, if you record it over time, and that allows you to measure the pulse. And that's exactly an application I'd like to do for you today. That's the first one. So the required steps are video acquisition, face detection, skin detection, video stabilization, color processing, and signal processing. And you'll see what I mean by all these topics as we go. All right, so first task would be to record. Now previously, or we still have, a command that's called current image, by which you can record a single image or a whole sequence of images from your built-in camera. But since we have the connected devices project, we can connect to all kinds of devices, and as such also cameras. So the way to proceed would be to first find the cameras that you have available, and you get here, in this case, just a single camera object that's built into my computer. Then I can select that by saying I'd like to have that first device. I can connect to that device by saying open it. I can request all the different properties of the device. I can have here, for example, frame rate. Currently it's set to 12 frames per second. I have raster size set to 320 times 240 pixels, and so forth. Well, the raster size I cannot really change. That's fixed with the hardware. But the frame rate I can change, and I'll change it here to 18. And then if I would like to record a little video, I would simply, well, just let's make it here a little less than that. Let's take 30. I can go like this and record it. And then I can close the camera connection, and then I can just animate what I've just recorded. And, well, it's not, well, it doesn't show very well, unfortunately. But since I anticipated something like this, and you don't want to risk anything like for a talk like this, I, of course, went ahead and recorded some video at home to actually do the measurement later on. Just mentioning here, for the measurement of the pulse, I also need the timing of the frames. So I have to extract the time stamps from every frame that we have, and that information is stored in the meta information of every image. So this is a little command, frame time, that takes basically the absolute time option stored in the meta information of the image, and you can apply that now to the video, and then you get the times by which, at which these frames were taken. So we start at time 0, and then 2 seconds down the road, 2 milliseconds down the road, first image, and so forth. All right, so this would be the way to record. And now, since I don't want to record but play it safe, I also have ways to import videos. And here I have one stored on my hard drive. I can visualize that with list animate. So that's me after jogging in front of the camera. That gives you a good heartbeat at least. And of course also I recorded the times, and these are stored here under video TS now. Okay, so step 1 is achieved. We have the data inside. Now we have to actually process the data. Okay, first of all, we have to find the face in the video, and that is really simple. That's a straightforward use of the find faces command in Mathematica. So find faces applied, for example, to the first frame of the video would simply give me a bounding box. This is the lower left corner of the bounding box. This is the top right corner of the bounding box. And basically I can visualize this, and you see it is pretty robust in detecting the face in the image. So I have to apply that to the whole sequence of 120 or so, 180 images. That takes a little while, so I have to wait here for a few seconds. And then what I have to do, I have to take an average box size. I don't want to have the frame of the face changing in size constantly. So what I come up here is a size of 90 times 144 pixels. Then I have to figure out where the position of that box is in the image, and I'd like to regularize that a little bit as we go in time. So I apply a Gaussian filter on the time axis. And then I extract now from the video just the part of the face, and what I get is this here. So just a small portion of that image now is what I need to measure the pulse. Okay, having that, I have to now stabilize the video because, well, I don't want to switch back now, but if you would have looked closely, there was still some jitter because the face detection is not meant to be extremely stably positioned in the video. It just locates the face, and that face may move, or the face detection may have moved slightly. So what I have to do is I have to actually stabilize the video, and that means I have to find the geometric transformation from one image or one frame to the next, and that's exactly what I do here by using the find geometric transform command. That command basically takes two images, one here and one taken here by this double hash, which is always a respective frame, and I have here a linear fitting or finding mechanism, and I only look for translations. I don't make this more complicated by also taking, for example, rigid transformations or perspective transformations into account. Okay, so I have done that already. Then I can apply that phase shift to all the faces, and eventually I get a stabilized version of the video. You can now see that there are some black margins popping up, but basically the video is stable. It doesn't move around anymore. Okay, so because simply you don't want to have any motion artifacts messing up your signal. And then the next thing is I have to detect the skin in the image in order to measure the slight change in skin tone. And I don't want to basically detect my eyes or my hair. So I'll again take the first image here. And now in order to develop a kind of a skin classifier, I would have to first by hand give it a ground truth, tell it what the skin looks like, and so I can generate a mask. And I'd like to do that by hand interactively. I just click on the image, and by hitting the control, oops, no, I want to have it. That's bad. Oh, okay, presentation mode is the problem here. How do I get out? Oops. Still in presentation mode, okay. Environment working. So now I'd be working on this slide, and I just click on the image, and you get what's called down here an image toolbar. This image toolbar allows you to interactively manipulate or extract features from the image. And what I'd like to do here is I try to create a mask for that image. So I hit here the mask tool part, and it opens up all kinds of tools. I can make points, lines, curves, specify rectangles, and so forth. And I can also have here freehand regions that I can specify. So I would go up here and specify part of the face as a mask to read off the color of my skin, like this. And then I can say here, copy this as a mask. I'm done, and then that way I could paste in here my mask that I have created that way. So I've done this fairly sloppy, so I'll just use the prepared one that I prepared for this talk. So this is now a black and white, a binary image that just specifies the region of my face, that's that is skin. Okay, so the way, or typically a skin detector just works by looking at the color of a pixel. If the pixel has a typical skin color, it's it's okay. If not, then I have to dismiss it. So what I do here is I have here a chromaticity plot, a new function in version 10 that shows me in the color space how the skin tone is distributed. Here you see the skin color, here you see the background color. And obviously, here again, the skin color, this is not a very nice distribution. So it's pretty important to pick the right color space, also for other reasons. For example, RGB is device dependent. You get a different color space when you switch from one device to the next. A device independent one, for example, is lab color, LAB color. It has a color metric that adheres to perceived color distances, and also has a nice separation between color and brightness or lightness. So if I use that color space, I get a much better distribution of my skin tone. Well, this is just a skin tone. If you just look from above, you see it's just one color. And that I can extract very nicely by reading out here the average position of that color, by looking at the standard deviation of that color, and then I put all of this here in a little compiled command that basically, with a Gaussian distribution, gives me 1 if I'm in that area of skin color, and it decays exponentially if I'm outside. So that's a skin classifier. I can apply that to the image, and you see it picks up the skin color fairly well. And I do that now for all images. I convert them to lab color, and I generate here an average over all frames to have a kind of a mask awaiting for reading of the skin color. And that's exactly what I do here. I just use image measurement, read of the mean color, the mean over all pixels, masking this with the skin weight that I just generated. And these are the measurements, the LAB color tone of the skin for each frame. And then I just can plot this, and darn, I don't see any pulse. That's a bummer, which basically would mean that this whole project goes down the drain, but I can look more closely. This, by the way, up here is the lightness or brightness. Well, I don't assume to shine up to become brighter or darker. I assume to just go a bit more reddish or more greenish. So I look here at the A, B, the color components more closely, and well, they do wiggle around, but still no pulse. So I have to work a little bit further. I have to basically unmix that signal. I have to do a kind of an independent component analysis. And this one I can do interactively, even because this is, only has one parameter. I have to mix between those two signals. And if I change here the angle, the mixing angle between these two signals, suddenly I see, oh, this looks pretty much like a pulse. Bang, 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 bang. So you could imagine that this is a very noisy pulse that I have here. And I can look here for the ideal mixing angle by trying to find the minimum for a signal that has a very small differential volatility. So that's the angle, and if I just apply this, I get this signal. So that's my signal. Actually, you can see two signals here. You can see the heartbeat and the breathing that goes up and down. Okay, so we have to extract that. I'll do this now with a bandpass filter because I know that my heartbeat should be something between 30 beats per minute and maybe 180 or so, something in between that. So I have here a bandpass filter that is tuned to that frequency range and thereby regularizes the signal a little bit, but not too much. So I get an even better heartbeat. And then I can use a new command like find peaks that allows you to read off the peaks in the data set. Well, these are the peaks that I get. Then I do, because I have to still gauge the time axis, I have to get a function that relates all the frame numbers to the respective times. I map that to the peaks that I have here, take the time differences, so these are the time lapse between every heartbeat, and then I can read off here my heart rate. Okay, and even use Mathematica's built-in quantity to give units to that. So I have here a heart rate of roughly 1.37 hertz, which means I have 82 beats per minute, and here variation, something between 70 and 100 hertz or 100 beats per minute. Now that's not inaccuracy of the measurement, but simply a fluctuation of my heartbeat. Okay, so this was a kind of a 2D example, and since the time is ticking, I quickly move over to a 3D example, which I'd like to hurtle through now. As I said, this has really up-to-date meaning to me because I injured my knee last Saturday. This is my knee from 10 years ago. It is an MRI scan, and as of version 9, we can now nicely handle volumes as well in Mathematica. You can not only visualize it by opacity, but you can also interactively now walk through here with a clipping range to visualize different parts of the knee, for example, like this. Okay, so if I, for example, do the same here with a manipulate and go through slice by slice of my knee, I see that clearly it's dark initially, it gets brighter, it gets dark again, so apparently I have a fluctuating brightness in my data stack, which I have to equilibrate. I quickly skip tomography as such, and oh, by the way, I should go back to the environment presentation mode. Here we go. And what I try now is to equilibrate the histogram of every slice. So I do kind of a histogram equilibration, but since the slice from slice to slice, the image changes slightly, I cannot just do an equilibration. I have to basically define a distance between histograms and make sure that the distance gets as small as possible. So this is the histogram of voxels of one slice somewhere in the middle. And if I have to go now to the next slice, I'd like to have a similar histogram. And I only change the histogram by scaling it. So I can do something like this here. I basically have now all the histograms in 3D. So this is the direction of slices. This is the histogram density. And this is the whole thing seen from above. Okay, and you can clearly see it gets darker down here, it gets brighter in the middle, it gets darker down here. So what we have to try to do is to basically get this aligned to make this straight. And I do this by defining histogram scaling, which I, by the way, do here with array resample, a new command in version 10 that allows you to resample data sets or bins. So I need to basically rescale histograms from one slice to the next by moving the scale. I do so by minimizing here a weight function for the histogram distance. This is applied in the scaling factor function where I try to find the optimal scaling. I apply that from one frame to the next, or from one slice to the next, and then thereby I get these kind of scales. It takes a bit. And this would be the rescaling factor as I go across the slices. I apply that to the data set, and you can now see that the data set has equal brightness. It doesn't change in brightness anymore. So that would be a typical pre-processing step, and we can just quickly verify. Okay, here we go. That was the case before the histograms, and this is now afterwards, and we see that we have gotten a slightly better distribution in color. So here, this is, by the way, the density of bone tissue or skin and fat tissue. This is the density of muscle tissue, and this is free space in that set. And what I do now is I try to segment. Segmentation is one of the big tasks in image processing when you want to extract certain parts of the data. And what I try to now segment is a bone out of that data set. So I can do a first rough segmentation by using one of the many segmentation commands that we have in Mathematica, that's clustering components, which basically does nothing else but a clustering algorithm applies that to the pixel color, and then you could see, okay, here I have the red part, that's the flesh, skin and bone is green, and then light green is empty space. Okay, this is, whoops. This is still a wrong data set in here. So this is now just the part of the segmentation that I just got of bone and fatty and skin tissue. And out of this, I'd like to then get the actual bone tissue. And I do so with that with some morphological operations. I basically do an erosion that I just shave off pixels or voxels from my segments I do so by taking off layers of 6 voxels, and that leaves me just with the core of the bone. All the other tissue basically gets shaved away because it doesn't have the appropriate thickness. And then I just add again a layer of 2 voxels to have a kind of a bone core by which I start now my next segmentation.